across all sectors is increasingly dependent on complex, interconnected ICT systems, making cybersecurity assurance more challenging than ever. Traditional assessment methods struggle to keep pace with systems that are dynamic by design. In Project COBALT, the concept of the security digital twins offers a new approach, enabling meaningful digital representation of ICT assets and their security state. Today, we are joined by Adrià Asensio from the Advanced Network Architectures Lab at Universitat Polite de Catalunya to discuss the security digital twin, its role in cybersecurity assessment, and its potential impact on future certification and standardization.
Dear Eleni, thank you very much for the introduction. The security digital twin, as defined in COBALT, is a virtual replica of an ICT asset that acts as a single source of truth for its security posture. It mirrors the asset's state by ingesting and correlating security-relevant data such as software components, configurations, running services, exposed interfaces, dependencies, and contextual information. What makes it meaningful and operational is that it does not simply inventory assets, but it models the security state in context. For example, in an AI lifecycle scenario, one security digital twin can represent the on-premises environment used to train the model, capturing installed libraries, services, logs, and data dependencies. When the model is deployed in the cloud for inference, a new twin is instantiated to reflect that specific operational context, including virtual machine configurations and deployed components. By doing so, the approach creates a digital thread across the asset's lifecycle. Security monitoring and assessment services can operate on the twin rather than directly in the production environment, enabling anomaly detection, risk evaluation, and change impact analysis without disrupting normal operations. In essence, the security digital twin provides a structured, continuously updated, and lifecycle-aware representation of ICT assets, enabling proactive and operational cybersecurity management. In COBALT, the security digital twin is grounded in the concept of a stored representation as defined by the Digital Twin Consortium. This means that the twin maintains a structured and persistent representation of an asset with focus on cybersecurity relevant attributes. To formally describe the internal composition of an asset, COBALT leverages standardized bills of materials based on Cyclone DX. Through software bombs and vulnerability bombs, and also cryptographic bombs, the security digital twin can represent software components, known vulnerabilities, and cryptographic elements in a machine-readable and interoperable manner. In addition, COBALT integrates the IETF manufacturer usage description specification and its extensions to describe expected network behavior and communication patterns. Together, these elements enable the security digital twin to mirror both the internal structure and the external behavior of an asset in standardized ways, supporting automated analysis, compliance verification, and continuous cybersecurity assessment. Well, beyond the standardized artifacts such as SBOMs or mood profiles, a security digital twin becomes truly effective when it incorporates dynamic and operational data that reflect the actual runtime behavior of the asset. In particular, system and application logs are essential to capture security-relevant events, errors, and anomalous activities. Network telemetry, including traffic flows and connection patterns, provides visibility into communication behavior. Runtime information offers insights into the current operational state of the system. Additionally, configuration data and security policy settings are crucial to detect deviations from secure baselines, while identity and access management data help assess potential misuse of privileges. Continuous updates on vulnerability status and patch levels further enable accurate exposure assessment. By combining these dynamic data sources with structured representations like SBOMs, the security digital twin evolves from a static inventory model into a living operational representation of the ICT asset, capable of supporting continuous risk evaluation and timely detection of anomalous or malicious behavior. The concept of security digital twin as a service is a fundamental pillar within COBALT. The as a service approach refers to the capability to instantiate or reinstantiate a security digital twin on demand in order to recreate either the current or previous state of a given asset. This capability is particularly valuable in the context of cybersecurity assessment, compliance verification, and auditing processes. By enabling precise reconstruction of an asset's state at a specific point in time, the security digital twin can provide evidence for both internal and external audits. To illustrate this with a practical example, consider a scenario in which multiple operational assets must undergo a security assessment. Instead of interrupting and interfering with their normal operation, a dedicated security digital twin is instantiated in parallel. First, this instance reflects the most recently assessed state, and then it is synchronized with the current operational state. The cybersecurity evaluation is then performed on the security digital twin rather than directly on the live system. Such an approach enables two complementary assessment strategies: a full reassessment of the system state or differential assessment focusing only on changes introduced since the previous evaluation. In both cases, the process ensures that cybersecurity analysis and assessment replay can be conducted without disrupting ongoing services. From my perspective, the main advantage of using security digital twins in cybersecurity assessment and certification is that they provide a high-fidelity, continuously updated virtual representations of the system under evaluation. In this context, high fidelity is crucial because certification decisions depend on an accurate understanding of configurations, software components, dependencies, and exposures. A security digital twin can serve as a reliable single source of truth for the security-relevant state of the system. One key benefit is that the assessments and analytical service can operate on the virtual replica rather than directly on the production environment. This reduces operational risk and disruption. Also, it enables a shift from periodic certification to a more continuous approach. When a component is updated or a configuration changes, then the twin reflects it immediately and can trigger a target assessment. Instead of reevaluating the entire system, certification efforts can focus specifically on the affected assets. Security digital twins are also valuable for vulnerability management. When a new vulnerability is disclosed, the twin allows rapid identification of impacted components. Potential mitigations can be tested in the virtual environment first, making it possible to evaluate their security impact before deploying in the real system. This supports more risk-aware and evidence-based decision-making. However, there are challenges, such as that of maintaining high-fidelity synchronization between the real system and its twin, since it's really technically demanding. Well, first, maintaining continuous synchronization between the real system and its digital counterpart is technically demanding and resource-intensive. Designing, implementing, and operating a high-fidelity security digital twin requires significant computational, storage, and networking resources. Moreover, constant synchronization might introduce unnecessary complexity if not carefully scoped. For this reason, it is essential to clearly define which elements must be mirrored, at what level of granularity, and at which frequency they need to be synchronized. Without this careful balance, the security digital twin risks to become impractical. Second, a security digital twin must integrate information from diverse sources, often in different formats and with varying semantics. In addition, the twin should support multiple analytical and assessment services operating on top of it. This makes interoperability and standardization critical to ensure consistent data exchange and meaningful interpretation. COBALT addresses these challenges in several ways. The security digital twin as a service approach minimizes resource consumption by instantiating and operating security digital twins on demand, specifically for cybersecurity assessment or certification activities rather than maintaining permanent high overhead replicas. To promote secure and reliable interoperability, COBALT leverages standardized data exchange mechanisms such as connectors aligned with the IDS. Moreover, for modeling the security-relevant state of assets, COBALT aligns with the object model defined in Cyclone DX and incorporates concepts from the manufacturer usage description specification. Furthermore, the overall architecture of the Security Digital Twin is designed in alignment with principles proposed by the Digital Twin Consortium, ensuring conceptual consistency with broader digital twin standardization efforts.
Thank you for sharing these insights into the Security Digital Twin and its role within Project COBALT. As ICT systems continue to evolve in complexity, approaches like SDT and SDT as a service offer promising pathways toward more dynamic, reliable, and scalable cybersecurity assessment. The work led by the UPC and the Advanced Network Architectures Lab contributes directly to shaping the technical and standardization foundations needed for future digital assurance. Thank you all.